Hello, everyone. Good afternoon. So it's my pleasure to introduce Professor Arvind Ayyer of IISc Bangalore. So he'll be telling us about inhomogeneous q-deformation of the Tsetlin library.
Thank you. Thank you for the introduction, and thank you to the organizers for inviting me to this very nice conference. I admit to being somewhat of a misfit here, in the sense that I'm not a geometer, but I will tell you something that I think you might find interesting, where we are studying a probabilistic model, and to our very pleasant surprise, something about the geometry of flags helped us solve the problem. Unlike most of the talks we've seen so far, these are flags on finite field vector spaces. So situation is in some sense simpler, but we'll see. Yeah. So yeah, and it's an honor to speak in a conference in the honor of, in the celebration of Professor Lakshmi Bai. So this is joint work with Anna Schilling at UC Davis, Sarah Browner, who's just joined UPenn, and Jan de Geer at Melbourne. So the first part of the talk is about a probabilistic model called the Tsetlin library. This is the same Tsetlin as Gelfand Tsetlin, so you can rest assured. Then this is a classical model which he introduced and was very well studied in theory of semigroups, in theory of Markov chains. I'll describe its q-deformation, and then I'll state the main results, and I'll tell you how flags. So we'll describe the flags, and we'll describe a Markov chain on the flags, which help us solve the original model. Okay, so I know it's a lot of work to come on an afternoon for just one talk, so I'll keep it light. Okay, so imagine that. So we'll consider the simplest possible model of a library, maybe a poor man's library or poor woman's library. Let's not be sexist. So you have a single shelf. Your entire library consists of a single shelf, maybe something like that. And you have n books, because we are mathematicians, we'll just call them 1 through n. And so the state space of our model will be all possible arrangements of books on that shelf, which of course is the set of permutations. Now, what you will do is you will only allow a patron to pick up one book at a time. So one person picks up a book, you will not let anybody else pick up another book until they return the book, okay? And the idea is that each book has a certain popularity index. Let's say some books are more popular than the others. And so you choose book A with some probability x sub A. For us, we will take these as formal variables, which x sub A sum to 1, right? x1 plus up to xn sums to 1. And then you pick the book A from wherever it was. And when you return it to the front. Okay, that's the idea. So you randomly pick up a book, you read it, and you return it. And then somebody else picks up a book, you read it, and you return. And so, as you can imagine, more popular books will tend to be at the front, right? Because larger the XA, the more likely it's to be picked up, and the more likely it's. Okay, so it's a very simple model. I hope the model is clear. So the surprise, okay, so let's do the first non-trivial example on 3 books. So these are permutations of the S3. So let's, for example, look at 2, 1, 3. With probability x2, you go back to itself because you put the first book, the book number 2, which was in the first position. We went back home. If you picked book 3, then 3 from the end moves front and you come over here. If you pick book 1, then 1 goes to the front and you get the identity. Okay, so that's it. So this is the model. I mean, why should you care? I mean, this seems like some arbitrary model somebody has proposed. So here is the transition matrix, okay, whatever it is. So the transition matrix just records, so it's indexed by the state space. And the ijth entry tells you the probability of going from configuration I to configuration J. Or if you want sigma tau entry, goes from sigma to tau, the sigma and tau permutation. So you can see row sums are 1 because x1 plus x2. And so if you look at the stationary distribution, that's the first surprise, that the formula is very nice. So since you may not all be familiar with probability, let me just tell you what is going to happen in general. So you keep doing this, you keep picking books, putting them back, etc. In the long time limit, what is going to happen is that each configuration in your state space, in this case permutations, is going to have a certain probability of being seen. Okay, and these will be, because this is a finite state Markov chain, by some general abstract nonsense, this will be a rational function of the xi's. And in general, there is no reason to expect it to be something nice. But here it turns out, at least in this example, if you compute the stationary distribution, which is the row eigenvector with eigenvalue 1, it turns out to have this very simple expression. And in general, so let me say something about the general situation. So you see what, in terms of permutations, what is happening? This, the fact that you pick a book, a book at some position, move it to front, is the action of a cycle, right? It's not a transposition, but it's a cycle. It's a cycle that starts at 1 or ends at 1. Okay, so in the usual, our usual notation, Si is the transposition that interchanges II plus 1. We are acting, we are post-multiplying. So you first act by Si minus 1, then Si minus 2, etc. And then you act by S1. So that's the action of taking the book at position I and moving it to the front. And this chi operator will just pick out x sub pi I. Okay, so it will just take that value. So this T is the generator, curly T. It will remove pi hat I and move it to the front with probability x sub. So that's all it is. So Tsetlin proved, and later Hendricks rediscovered in a very cute 3-page paper, that the stationary distribution has this beautiful product formula. So it's the probability of seeing any permutation pi is x sub pi 1 times x sub pi 2, etc. You just multiply them on the top. And on the denominator, you take x sub pi I plus 1 plus etc. up to x pi n. So you take the suffix sum. Okay, and you take this product. Now it's not, notice that the denominators are different for different permutations, right? So, but it's a probability distribution, which means they sum to 1. This is not even obvious for S4, if you just want to see. I mean, these denominators are wild. I mean, there's no. No, 3. Right. So, okay, I was cheating. So I have assumed x1 plus x2 plus x3 is 1. So I've removed it. And the first factor will be x1 by x1, so that will cancel. So there'll be only 2, n minus 1 non-trivial. Yeah, I've just, because it's cleanest to write it. Okay, so this, this is such a simple system, and it has given rise to lots and lots of generalizations. And in particular, so I cannot survey all of that. There's, just to say, they're like, you can generalize to multiple, libraries with multiple shelves, of course. You can generalize to libraries on trees. There's all kinds of things. There are books on these. Anyway, our point of view is to look at geometric finite semigroups. This was initiated primarily by Diaconis and Brown. And then we have done a lot of work in this direction. So we generalize this to arbitrary posets, etc. So there's some long story. Okay, so I'll tell you what the semigroup formulation is. So you have the set of subsets of 1 through n, and we we make it a semi-group by defining a multiplication operation, which just is the union. Okay, so there's no inverse obviously, so it's a semi-group. And this semi-group is very special. It forms something called a left regular band. So, and the property is that U is an idempotent. So U times U is U, which is of course clear. A union A is A. And then this very nice relation, U dot V dot U is U. Okay, one can check this, it's not. Okay, and then if you look at the Cayley graph of this semi-group with generators singletons, then of course you get the Boolean hypercube and with directed edges. So that's not difficult to see. And so you start with the empty, you multiply by 1, 2, or 3, and then etc. You continue. Now, why does this help us? This helps us because in this theory of semigroups, there's something called a Karnofsky-Rhodes expansion. So what you do is you start with the empty word. Now, we are going to multiply by these generators 1, 2, up to n, in this case 3, this example. And each time you multiply by something that's not already there in your word, you go down, you descend. And if it's already there, you go back to yourself. So now, so for example, you start with the identity, you multiply with 2, then you again multiply with 2, you stay there, then maybe you multiply with 3, you go down here. Now if you can multiply by 2s and 3s, it doesn't matter. At some point you multiply by 1 and you are here, right? So then the advantage of this formalism is that the moment you reach here, you are at stationarity. So, I mean, for people like Hari who know about mixing times, this will tell you you're exactly in stationarity when you reach the bottom. Okay, so it's very useful for computing things like this. Okay, so yeah, so in general, one will work on this minimal ideal, which is the permutations, and the random walk on this minimal ideal is exactly the same. Okay, so there's some trick which relates going from this whole picture to a Markov chain on this minimal ideal, and it has to do with left and right multiplication. Sorry? This is the minimal ideal of this semigroup. Yeah, because all of these are acting on it. Okay. And so there's a unique simple path to any permutation in this left regular band. And any path which leads to pi is of this form. So first it will act by pi 1. Then you can apply pi 1 any number of times. Then you act at some point by pi 2. And then you can act by pi 1 and pi 2 any number of times, etc. You continue this way. And you will eventually hit pi. And the point is that the stationary distribution is exactly the probability of starting at identity and getting up to there, where you assign probability xi to multiplication by I. Okay, so this essentially is the proof of this formula. Yeah, it's very, very nice. So this was I think originally due to Schützenberger. I mean, the definition of the left regular. But the other nice property of the Tsetlin library is that the eigenvalues of the generator, the matrix, for example, that I showed you on S3, is also very nice. So for every subset of 1 through n, let's say of size k, there is an eigenvalue which is given by x. If S is I1 through ik, then I have an eigenvalue xi1 plus up to xik. And the multiplicity of that eigenvalue is also explicit. It's precisely the number of derangements of size n choose k. So remember that a derangement is a permutation without fixed points. So in this example of the matrix I showed you, there's the eigenvalue z0 occurs twice. x1, x2, x3 each occur once, and the sum is of course the Perron eigenvalue in that. Yeah, and notice that there is no x1 plus x2. Why? Because D1 is 0. There is no derangement on of size 1. So that's it. Okay. So, this what we are going to present is one more generalization, and this is in the direction of Hecke algebras. So you know that the SIs satisfy the bladed relations, and there's a q deformation of it, which leads to the Hecke algebra. And this is, there are many conventions. So this is for how to insert the q, and this is how we add it. And this q analog was studied recently by these people, among whom Sarah is one of the co-authors. And again, the idea is similar. You act by the TIs in exactly the same way that I showed you. And this time, if you act, so the Hecke algebra also acts on CSN, the group algebra of SN, and it acts as follows. So TI acts on pi by permuting I and I plus 1 with a factor of q if pi I, if there is a descent. Otherwise, there are two components, either it flips or keeps it invariant. But the key point here to notice is that the sum of the coefficients is q. So if I divide by q, this acquires a probabilistic meaning, right? So it's either with probability 1 you flip, or with probability 1 over q you flip, and q minus 1 by q you keep the same. So there's, so here, of course, q is going to be a parameter, but we'll change that point of view very soon. But we keep this in mind, that we need q inverse to be less than 1 because of our future interpretation. So this was their generator, this TQ. And what we do now is to make it inhomogeneous by adding these parameters x sub I. And this was sort of non-trivial to do, because one wants the quote unquote niceness to continue. So the thing was, after playing around, we realized that the correct way to insert the parameters, the inhomogeneous parameters x1 through xn, was to add them in this particular way. So the idea is, you act by this product ti1 through ti through t1, sorry, and at the end, whatever permutation you get, this is a typo. It should be pi 1. I apologize. So this should be q to the pi 1 minus n times x sub pi 1. So when you have done all these operations, you get some linear combination of permutations, and to each of them you associate something corresponding to the first entry in that permutation in one line notation. Okay? And again, we want the sum of the xi's to be 1. So here, now you see the matrix is going to look quite horrible. So again, row sums are going to be 1. For the first 2 rows, it's clear, but then on first 3, it's clear actually. And then, things start to get messy. So there'll be this q inverse factors, in some cases even q inverse squared and so on. This will appear. But I mean, basically because of the way we engineered it, it's guaranteed that the row sums are 1, even though it's not. And okay, so I want to tell you 2 results which generalize the Tsetlin library. One is for the stationary distribution. Again, you can keep applying this, you can run this Markov chain many times, and you're looking at the row eigenvector with eigenvalue 1. So that's the stationary distribution. To define the stationary distribution, take some notation. So let inv pi be the number of inversions, which is all know. This you may not know, but it's not difficult to define. A left to right minimum in a permutation is an element pi j such that it's the smallest when you read from 1 through j. Okay? So that's why, okay, these things occur in statistics, for example, records. And we let LRM be the positions of left to right minima. So here, for example, So the, okay, sorry, I think I didn't fix this typo, so yeah, we should correct this. Is it okay? No, I think it's messed up. So it's the positions, not the values. That's why I made a mistake. Yeah, 5, 4, 2, 6, 3, 1, 4, 6. This is 2 4s. Okay, it should not be. Okay, let's just take this. So the first entry is always a left to right minimum. The second one is smaller than the first, so it is as well. So I have 1, 2. Then the third one is as well. And this is not, but 1 is. So yeah, so ignore that line. Okay, and then we have some function kappa, which takes a weakly decreasing tuple of integers, in which now for us it's strictly decreasing, and you get some linear combination of the xi's. And for an arbitrary tuple, you have kappa as just kappa of the weakly decreasing version of that sequence. And then we have this explicit product form of the stationary distribution. That's our main theorem. You know, it's complicated to read, so I'm not going to ask you to read, except that it contains this function. Okay, so that's the first theorem, and I'll give you an example in a second. The next theorem is a generalization again of the Tsetlin library, where we give the eigenvalues. So for any subset of 1 through n, which we order in decreasing order, we get an eigenvalue which modulates each xi with some power. And again, the multiplicity is exactly the same, the derangement. And to give you an example, so going back to the same example, the eigenvalues are, you see these two eigenvalues have their values modified by q, and the stationary distribution looks like. So some factors are modified by q. Yes, q is assumed to be greater than 1 because of so, sorry? No, q inverse has to be less than 1. So, I mean, as I said, we'll deal with finite fields and then we'll be fq. So the q will be a prime power. So the surprising thing for us was that, you know, after we found it, we tried to prove it directly on permutations. And this, in principle, does not seem to be so hard because, I mean, this is, you have a candidate. So all you have to do is to verify that it's a left eigenvector with eigenvalue 1 for this matrix. So it's not, maybe it doesn't seem that hard, but, you know, we could not get it to work in any easy way. So our proof is completely using this finite field geometry. So just to summarize, this is our most general q-Tsetlin library. When you set q equal to 1, you get the Tsetlin library that I began with. And if you set xi equal to 1 by n, you get the homogeneous version, which was in this other paper from last year. Okay. So now maybe I'll go a little fast over flags because all of you know more about it than me. So we'll work with finite field q elements. And so a flag, as you know, is a sequence of subspaces, one contained in the other. And the set of all complete flags is, of course, G mod B. And where you have a flag of each, a vector space of each dimension. And the standard flag is given in terms of E1, E2, etc., where EIs are the standard basis. So the number of lines, so lines are going to play an important role in our story. So you might know the number of lines is the q analog of n, is q to the n minus 1 by q minus 1. It's the same as 1 plus q up to the geometric series. And the number of flags is the q factorial of n, which is just the product of, so this nq factorial is nq times n minus 1q. Okay, so just to give an example, here, if you have n and q both 2, then you have 2 sub 2, which is 1 plus q, which is 3 lines. And these are E1, E2, and E1 plus E2. There are no coefficients because q is 2. And there are 3 flags. I will use flags to mean complete flags. There's E1 contained in E1, E2, E2 contained in E1, E2, and E1 plus E2. I mean, E1, E2 is the whole, is F2. So there's only one, I mean, these two are essentially the same. But we need the, what's it called, the coset, double coset representative. So that's why I'm writing it this way for these flags. Okay, so again, you know that because of GLN, these flags are represented in terms of equivalence classes. And for GL3, for example, there are 6 equivalence classes corresponding to the permutations. And so here I'm taking the convention that above a pivoting one and to the right of a pivoting one, all the entries are zeros. So for the identity, there are three elements. For the long word, there's only one. So the relation between the Tsetlin library and the flags is through this very nice result of Halvorsen and Ram from 99, who showed that the Hecke algebra with that Q, the parameter Q now is the prime power Q. It acts on a flag by the following. So if I take T sub I, it acts on a flag by replacing the ith vector space by a sum over all possible vector spaces of dimension I, which contain Vi minus 1 and are contained in Vi plus 1, but are not equal to Vi. So if you make this sum, so I should say we are working over C of G mod B, right? The group algebra. So this is a sum in that space. So they realize that if you define it this way, then this Ti satisfies the fundamental relations of the Hecke algebra. And so, for example, if you take in this GL3FQ, you have this flag which is E3 contained in E3, E2, and which is represented by the double coset for 3 to 1. Then when you act by T1, you will sum over everything which is contained in E2, E3, because by this definition, it has to contain empty, okay, that's fine, but it has to sit inside E2, E3. So, but it should not be itself. So if you reparameterize after left multiplying appropriately, you get this sum. And so this is exactly the Hecke action, because there are Q elements here, and what you did is you changed 3, 2 to 2, 3. This is exactly the definition. And similarly, there's you can check the other case when you have an increase, so you have an ascent, then you get what I showed you. Okay, so that's how the TIs are related to the flags. And now I can define our model. So the idea is going to be, I'm going to define an analog of the Tsetlin library, this time on flags. So this is again because we are on a finite field, so everything is finite. This will be a large Markov matrix. So what this new generator does is the following. So we are only going to add lines. Okay, so the idea is that we are going to add, V0 is of course empty. You add a line Lj with some probability, which I'll explain in a second, and then you add it to every other vector space. So you take the sum so you form the subspace with Vi and this Lj for each I, then you again get a flag. And at some point, you'll have some repeat, right? You'll get something where the dimension does not increase by 1. At that point, you just throw away that vector space. Okay? So you added Lj, which is of dimension 1. Then you have V1 plus Lj, which is of dimension 2, etc. Or if Lj is not contained in V1, and so on. At some point, the dimensions have to repeat, and that point you just throw it. So, and now what the key point is that you add line Lj with probability xi by q to the n minus I. If the line Lj, the first non-zero entry of that line is Ei. Okay, every line can be uniquely represented in this way, where the first coefficient is 1. You know, that's of course just a scaling. So, so this gives us a probability. So now, given a flag, I will add all possible lines, my n sub q lines, according to this distribution. Okay, and the nice thing here, and this was discovered by Ken Brown, is that these also form a left regular band. So the original strategy I told you about for the Tsetlin library continues to work. The whole same philosophy will work, and we will we'll be able to apply the same machinery. So this is just a repeat of the same line. So line Li has probability Yi, which is xi. So Brown actually studied exactly this Markov chain, which he called the Q analog of the Tsetlin library also. But in his situation, he gave different probabilities to each line, sorry. So each line has a probability, L has probability Y sub L. So completely independent. So this is of course much more general and in some sense much more powerful. But because it's so much more general, it misses the connection to the Hecke algebra. So so we still had to do some work to make to get the formula. So with regards to the stationary distribution, so he gets the eigenvalues that we use. But with regards to the stationary distribution, this is so much more complicated as a Markov chain that he doesn't have an exact formula. What he has is a sampling method. So, which is also nice. I'm not trying to put it down. Yeah, exactly. So I'll show you the formula for the stationary distribution. It involves this function b sub k of s, which is the number of elements in 1 through k minus 1, which are larger than s. Yeah, so it's also a product formula. It's complicated, but it's a product. And so here, as I take the same example, N3 and Q2, and here you see the formulas are just in terms of x size. Q is 2 in this example. And so the nice thing here for us, which is not true for Brown, is that every flag corresponding to a given permutation has exactly the same probability. So this factors 2s and 4s that you see will cancel out because there'll be so many flags of that size. Yeah. So again, if you look at the Karnofsky-Rhodes expansion of the Cayley graph, you have things like this. This is just a small part of the rather large graph and for arbitrary Q. So just to show you an example, look at this path, which first goes to E1 and then E3 and then E2. So this is the flag that we're looking at. So first you multiply by, okay, so let me show you. So first you multiply by Y1, and then you can apply Y1 any number of times. So you get this geometric series, which gives you 1 by 1 minus Y1. Then you can apply either the flag 3 or 1 plus 3. And now but you cannot apply 1. So you get a y3 for this 3. And for 1 plus 3, you get q minus, well, okay, so there's a factor of q here. So you get q minus 1 different things. That coefficient in front of 1 cannot be 0. So that's why it's. And then again, you can repeat 3's, 1's, 1 plus 3. So you get this bottom part. Yes, only the first, yeah, right. And you need that because the y is indexed by that, yeah. And then you repeat these 3 any number of times, you get this denominator, again geometric series. And now you can act by any of these 4 things and you get this. So you get some nice, so because of this, you get this product. And let me tell you about the eigenvalues. So there is it must, mercifully for us, someone had already worked out a Q derangement, Q analog of the derangement numbers. Actually, there are multiple. The one that's relevant to us is this one by Michel Vaux, again coming from finite field geometry. So this is if you set Q equal to 1, you get the usual derangement numbers. Yeah. I think, yeah, something like that. I've forgotten. So the eigenvalues again have the same form. So if you have any subset, which you write in weakly decreasing order, you get this linear combination of xi's with multiplicity now given by the derangement number times the power of q. Okay. This is for everything but the Perron eigenvalue. For the Perron, you get, which is just x1 up to xn, you get. And to go back to the same example, you get 0 6 times, x1 by 4, x2 by 2, and x0 8, 4, and 2 times, and 1. The sum. Okay. All right. So, so let me relate the two at the end. So there are actually 2 commuting diagrams that help us. So so our Markov chain, so this is the original Markov chain we wanted to study on CSN. And the strategy has been to build a more complicated Markov chain in some sense on CG mod B and apply a more complicated operator. But there are 2 things that save us. One is this projection operation and the other is this inclusion. So for the eigenvalues, we use Brown's formula for this G mod B, and we have this explicit inclusion map which we can show makes the diagram commute, and there's some technical blah blah which allows us to. So this part is in some sense the more non-trivial part, because I mean from some general arguments you can say that an eigenvalue which occurs here also occurs at the bottom, but we don't have control on the multiplicity. So to know what the multiplicity is, we need a map that kind of lifts the bottom Markov chain to the up Markov chain, and that's what this inclusion map. For the stationary distribution, we go the other way around, and there is this general notion of lumping, which is another word is projection. So suppose you have 2 Markov chains on 2 different state spaces. Let's say xn is a Markov chain on A and yn is on B. And suppose there is a surjection which goes from A to B such that when you sum over the, so okay, I've also defined the transition matrices in these 2 spaces. So you sum over everything in the, okay, so let me go slowly. So I'm looking at in the chain B. So for us, this is the chain on Sn. So I'm looking at this particular entry of the transition matrix, which is the probability of going from y1 to y2. So I go back, I look at everything for a fixed x1 which goes to y1. I sum over all x2s that go to y2. that sum over the entries on this larger Markov chain should come to the entry of the smaller Markov. If that happens, then if you run the Markov chain above and you just look at what's happening after this projection map, it will also be a Markov chain. The Markovian property will be preserved. If this property does not hold, in general, this is not going to be Markovian. Okay? It will not lose memory. You want this memory-less property. And if such a lumping happens, then the stationary distribution of the lower Markov chain is just the sum of all the things that project to it. I mean, the sum of the stationary probabilities of things. Okay, this is again abstract nonsense. You don't need much. Okay, and our theorem is that the Markov chain on flags in FQN lumps to the Markov chain on Sn, and the projection is the most obvious projection. I told you that every flag has a permutation representative. You just take that one. And all of those double coset representatives have the same probability, which all of those which project to the same permutation have same probability. So it's just power of Q that. Okay, all that is good. So, but this does not bring us home yet, because when we started this work, we are thinking of Q as a parameter. In the Hecker algebra, Q is just a parameter. It's some, as we said, Q inverse is some real number between 0 and 1. And now, to prove this, I have gone to some finite fields vector space, but there I am necessarily forced to assume Q is a prime power. So all I have shown so far is that there are infinitely many values of Q for which this projection happens, and therefore I get my theorem. But I want for all possible values of Q. And so there's one last step, and this is called the Markov chain tree theorem. So this is some yeah, so no, but one still needs that. Yeah, so it's not enough to say rational functions, because you want control on the degrees. Maybe it's okay, but the Markov chain tree theorem guarantees that these are polynomials up to some overall factor. These are polynomials in Q. For us Q inverse. So yeah. So we use this as an interpolation trick to get ourselves the result. And as I said, all flags associated to the same permutation have the same. No, this is for the stationary distribution. Yeah, so the eigenvalues I mentioned earlier. So here, so we use this inclusion. So here, I'm not getting into the details. It's a bit technical. But we need an explicit map like this. In general, if you just have this projection, you don't have control on the multiplicity. You know that if an eigenvalue is up there, well, in principle, it can vanish on projection. So you don't even know that it's there, but okay, one can sort of believe that it will be there below. But how do we know how many times it appears? For that, you need. So this inclusion allows us to build the transition matrix above from the one below, and that. Okay, so I'm done. I'll just end with the conclusion. So we constructed the stationary state and eigenvalues using this Markov chain on flags. And I'll also mention that without too much more work, we also have a generalization to words. So you can think of permutations as words where there's just one copy of each letter. But, or if you want one book of each type in a library, you can have multiple copies of books, of course. And so we fully understand what's happening if you have I books, if you have, let's say, S books with MI copies of the ith book for arbitrary MI. And there's again similar kind of. Okay, let me think. It's the same. So the ith book will still have an X sub I, same as before. I have to remember, I have to recall, there may be it may be tempered by some power of Q. So, so if I, okay, so since you asked and we have some time. So if I take a vector of multiplicities, M1, M2, etc., M sub S, right, and I take W sub M to be the set of all words with M sub 1 ones, etc., M sub S S's. Okay, that's horrible. Okay, maybe R. Right. So I'm going to act on C sub WM, and I have to first convince you that the Hecke algebra acts on this. So the okay, so go back. Yeah, it's not partial flag varieties. So okay, I'm coming to that. Let me answer Raghavan. Oops. Yeah, so you have to tweak this, and accordingly, so again for the ith book you will have X sub I, and there may be a power of Q here, which I cannot recall, but yeah, but it's not too difficult to figure out what. Yeah, to answer Amri's question, so you can lift this also, so this chain also to flags. So so the chain on, so if I call N to be, yes, exactly. So you can do it that way, right? So there are 2 points of view on how to get this. So if I write N as the sum, M1 plus up to MR, then the Markov chain on CSN projects to this. It's like identifying books. But you can also lift this to C of, well, okay, G mod B, where G is FL, G is FQ to the N, where, but now you have, you don't consider all flags. You still work with complete flags, but you only work with flags where there's a restriction on how they are ordered. And that has to do with how many copies of a certain book there are. So the first MI books will be in, first MI, E1 through EMI will be in certain order. So that will help. Okay, so I'm almost at the end. So I just want to say one more thing, that I repeat one more thing, that we don't have any proof directly in CSN. Even though the chain was defined originally, we had to go to these flags. And so in some sense, that was nice, and we enjoyed learning about it. But it would be nice also to have a direct. Okay, with that, I thank you for your
Are there any questions?
Standard, what about type B and
Yeah, so we have been thinking about it. Yeah, so it does not seem to be so easy. I mean, yeah, cycles. Okay. Yeah, so that there is, it is, I mean, okay, so let me go back to the diagram. Yeah, so if I look at the type, if I think of type B, over here, we have not found it in the literature, the analog of type B. I mean, in the sense, we believe it is there in some much more general version, but but it's not explicitly written as such. So we would want to first add a Q and then add the excise. So we don't yet know how to add the excise. I mean, there's some obstruction is there which we have not figured out how to do. Yeah, but we're thinking.
Are there any other questions?
This TQ and this TQ tilde are kind of semi-simple. I mean, they're
Yes, yes.
diagonalized. I'm just
Yeah.
curious, are these in the Gelfand-Tsetlin algebra, the Hecke algebra, or?
Oh, I don't know enough. No, but these are a left regular band. I mean, they're not even a group. Right? Yes. Right. No, but the TIs will, no, the TIs, of course, have the usual relation. I'm not sure what you mean. Previous, right? Where did you want? Tell me when to stop. This one? Yeah. No, but no. But these are the ones that I mean, if I look at all the operators that act by xi, I mean, for which you get xi, then they form a left regular band. So they satisfy the relations that I showed you earlier. So they don't even have a groups. Yeah, this relation they said. That's why we are able to do it. So maybe I'm not getting. Okay, yeah, maybe we can discuss. Yeah, I'm not sure exactly.
Are there any other questions? So if not, let us thank the speaker again. So we have a group photo session, if I'm not mistaken, at